While billion-dollar factories sit dark during power outages, one workshop in rural Vermont keeps machining precision parts using technology from 1890. No electricity required, no downtime, just water flowing downhill doing what it's done for a century. Before we continue with the video, if you're listening right now, help me prove something wrong. My wife said I wouldn't even reach 1,000 subscribers, but I believe stories about old machines like this deserve to be heard. Help me show her that these videos matter. Please subscribe to our channel and let's keep these old trains' legacies alive. The leather belt whispered overhead as Thomas Berkshire adjusted the mill's grinding wheel, water flowing beneath the floorboards like it had since his great-grandfather first diverted the stream in 1898. Outside, the modern world hummed with electric motors and digital controls. Inside Berkshire Machine Works, power arrived the old way, through a wooden wheel turning in cold Vermont water. Belt broke on that CNC mill again, Thomas called to his daughter Sarah, who was positioning a steel blank under the water-wheel-driven lathe. Third one this month. He gestured toward the corner where a silent machining center sat, its control panel dark, waiting for the electrician who'd promised to come last Tuesday. The water wheel outside turned at exactly 12 revolutions per minute, same speed it had maintained since William Berkshire engineered the system using principles borrowed from New England textile mills. The wheel's 16-foot diameter caught water from a mill race diverted from the Outaches River, converting gravitational potential energy into rotational force that powered every machine in the shop through an elaborate system of overhead line shafting. Sarah engaged the lathe's clutch lever, and the cutting tool bit into steel with the steady confidence of unstoppable momentum. No variable frequency drive modulating power, no servo motor, hunting for position. Just water pressure translated through wooden gears, iron shafts, and leather belts into cutting force that had produced parts for 3 centuries of American manufacturing. The shop's rhythm followed the river's flow rather than the electrical grid's frequency. When spring runoff swelled the stream, the water wheel turned with extra vigor, and the machinists adjusted their cuts accordingly. During summer's low water, they worked more deliberately, letting the reduced power dictate a gentler pace. The machines never complained about voltage fluctuations or phase imbalances because they'd never met electricity. Thomas walked the length of the shop, his footsteps echoing off maple floorboards worn smooth by generations of Berkshires. Above, the line shaft system stretched like a mechanical spine, 40 feet of rotating steel supported by pillow block bearings that had been hand-scraped to perfection in 1898. Leather belts dropped down at intervals, each one powering a different machine: drill press, metal lathe, surface grinder, milling machine. Every tool in the shop predated the Rural Electrification Act. The drill press was a 1904 Barnes model with a cast iron frame that weighed more than a modern car. The metal lathe bore a brass plate reading Reed Prentice Company, Worcester, Massachusetts, 1897. Even the newest machine, a surface grinder installed in 1923, had never known the touch of electric power. "Grid went down again in town," Sarah said, checking her phone. "Storm knocked out the substation. They're saying 4 hours minimum." Thomas smiled and adjusted the belt tension on his mill. Their shop would run regardless. James Francis never visited Vermont, but his mathematics powered the Berkshire wheel from 3,000 miles away. The Scottish-American engineer had perfected his turbine design in Lowell, Massachusetts in 1849, creating efficiency formulas that turned falling water into predictable mechanical power with losses under 10%. The Berkshire water wheel wasn't actually a wheel at all. It was a Francis reaction turbine hidden inside a wooden housing that looked traditional to satisfy local aesthetics. Water entered through a spiral case, accelerated through fixed guide vanes, then struck the turbine's runner blades at precisely calculated angles. The runner's rotation drove a vertical shaft that connected to the overhead line shafting through a right-angle gearbox assembled from yellow birch and bronze. Thomas explained the system to an engineering student who'd driven up from MIT, drawing diagrams on the back of a job order. The mill race drops 23 feet from intake to turbine. At 300 gallons per minute flow rate, that's about 3 horsepower delivered to the shaft. Francis's efficiency equations predicted we'd get 2.7 horsepower after losses, and that's exactly what we measure. The turbine spun at 240 RPM, far too fast for most machine tools. The right-angle gearbox reduced this to the line shaft's 60 RPM through wooden gear wheels cut by William Berkshire himself. Yellow birch was chosen for its density and self-lubricating properties. The wood's natural resins reduced friction while the grain structure absorbed shock loads that would shatter cast iron teeth. Each machine tool connected to the line shaft through a belt shifter mechanism, a simple device that moved leather belts between pulleys to engage or disengage power. Push the lever forward, and the belt climbed onto the driven pulley. Pull back, and the belt dropped to a free-spinning idler. No electrical switches, no electromagnetic clutches, just geometry and friction doing what they'd done since medieval watermills ground grain. The leather belts themselves embodied forgotten craftsmanship. Made from oak tan cowhide stitched with copper rivets, they lasted decades with proper maintenance. Thomas kept a belt dressing station in the corner. Neatsfoot oil, beeswax, and rosin mixed to a formula his great-grandfather had learned from a millwright in 1895. The mixture penetrated the leather's fibers, keeping them supple while increasing grip on the pulleys. "Modern shops chase power," Thomas said, running his hand along a belt's smooth surface. "They install 50 horsepower spindles when most cuts need 5. We work within what the river gives us, and the river gives us enough." The student photographed the belt dressing station, noting the glass jars with handwritten labels that predated plastics. The turbine's governor maintained constant speed through pure mechanical feedback, a spinning ball mechanism that adjusted water flow when loads changed. James Watt had invented the principle for steam engines in 1788. The first electric motor arrived at Berkshire Machine Works in 1947, delivered by a salesman from General Electric who promised to modernize their operation. William Berkshire, Jr. listened politely, then declined. His reasoning, preserved in a letter to GE's district office, revealed thinking that would prove prophetic. "Your motor requires fuel consumed elsewhere and delivered through wires that can fail. My wheel requires only gravity, which has never taken a holiday." Sarah pulled out the letter, now framed on the shop's wall, as she explained their philosophy to a journalist writing about resilient manufacturing. The journalist had arrived expecting a quaint historical curiosity and was slowly realizing he'd found something more significant, a working proof that industrial production didn't require the electrical grid's complexity. Modern machine shops consumed staggering amounts of electricity. A typical CNC machining center drew 30 kilowatts during operation, roughly the same as 20 American homes. Multiply that by a dozen machines running 3 shifts, add in HVAC systems to remove heat from all those motors, lighting for 24-hour operations, and computer systems managing production schedules, and a modest job shop could easily pull 500 kilowatts continuously. The Berkshire shop used 0. Their only concession to modernity was LED task lighting powered by a small solar panel Thomas had installed in 2019, and even that was controversial. Sarah argued they should stick with the original oil lamps. The economic implications compounded over time like interest in a bank account nobody checked. The shop down the road paid $4,800 monthly for electricity, nearly $60,000 annually. Over the 125 years since the Berkshire water wheel began turning, that would have totaled $7.5 million in operating costs. The Berkshire's only energy expense was occasional maintenance on the mill race and turbine, perhaps $500 annually averaged across a century. But the real advantage revealed itself during disruptions, when Hurricane Irene devastated Vermont in 2011. Knocking out power across the state for days, modern machine shops sat idle while their owners filed insurance claims. The Berkshire shop ran continuously, fulfilling orders for emergency equipment repairs as long as daylight lasted. The river had swelled with stormwater, actually increasing their available power. "We're not off-grid," Thomas corrected the journalist. "We're pre-grid. There's a difference. Off-grid means you chose to disconnect from something you once needed. Pre-grid means you never needed it in the first place." The journalist asked about productivity limitations. Surely the restricted power limited what they could produce. Thomas walked him to the completed parts rack, where precision components awaited shipping to clients across New England. Each part met print specifications within tolerances measured in thousandths. Each had been produced without consuming a single kilowatt-hour from the electrical grid. Fast and dependent or steady and autonomous, Thomas said. Every shop makes that choice, whether they realize it or not. Robert Williams could feel trouble in the line shaft before the bearing temperatures confirmed it. The veteran millwright placed his hand on the pillow block housing and sensed a vibration frequency that shouldn't exist. A harmonic that meant the bearing's babbitt lining had worn thin. He'd been maintaining the Berkshire shop's mechanical systems for 40 years, learning from his father who'd learned from Thomas's grandfather. The millwright's trade existed before electricians, before HVAC technicians, before industrial maintenance as a modern profession. Medieval European millwrights had built and maintained water-powered grain mills, saw mills, and textile operations using knowledge passed down through apprenticeships that lasted 7 years. Their descendants brought those skills to America, engineering the mechanical systems that powered the Industrial Revolution before electricity arrived. This bearing was poured in 1952, Robert explained to an apprentice who was learning the old ways. He disassembled the pillow block, revealing the white metal lining that formed the bearing surface. Babbitt metal, an alloy of tin, copper, and antimony, had the peculiar property of being soft enough to conform to shaft irregularities, yet hard enough to support rotating loads. Isaac Babbitt had patented the formula in 1839. The repair process required skills that most modern maintenance technicians had never encountered. Robert melted fresh Babbitt in a cast-iron ladle over a propane torch, pouring the molten metal into the bearing housing while it was still assembled around the shaft. The shaft itself, coated with lampblack and oil to prevent bonding, became the mandrel that formed the bearing's internal geometry. After the metal cooled, Robert hand-scraped the surface to create oil pockets, the same technique used in the 1940s Bridgeport but applied to rotating equipment. Each scraping stroke removed microscopic amounts of metal, creating a bearing surface with specific contact patterns that would distribute loads evenly while retaining lubricant. Electric motors made this knowledge optional, Robert said, smoothing the scraped surface with a burnishing tool. When a motor bearing fails, you buy a sealed cartridge and bolt it in. But these line shaft bearings, you have to understand the metallurgy, the geometry, the lubrication dynamics. Can't order these from a catalog. The apprentice watched as Robert reassembled the pillow block, adjusting clearances with brass shims cut from sheet stock. The final fit was checked by feel and by the sound the shaft made when rotated by hand. Too tight and friction would generate heat. Too loose and vibration would destroy the carefully scraped surfaces. Overhead, the line shaft resumed its eternal rotation, the repaired bearing whisper quiet, despite supporting hundreds of pounds of rotating steel. No bearing temperature sensors monitored its condition, no vibration analyzers predicted its failure. Just oil, metal, and the millwright's practiced hand ensuring another generation of service. The facility manager from a nearby aerospace subcontractor toured the Berkshire shop with barely concealed skepticism. His operation ran 30 CNC machines in a climate-controlled building where tolerances were measured in microns and surface finishes approached optical quality. The idea that anyone could compete using century-old belt-driven equipment seemed absurd. Thomas handed him a completed part, a bronze bushing machine from solid bar stock. The manager examined it with experienced eyes, noting the surface finish, concentricity, and dimensional accuracy. He pulled a micrometer from his pocket and checked the critical diameter. It measured 1.752 inches. The print specified 1.750 plus or minus 0.002 inches. Well, within tolerance. "What's your cycle time?" the manager asked, calculating productivity metrics in his head. Sarah checked the job log. 45 minutes from bar stock to finished part. We make about 8 per day when we run them. The manager's CNC lathe could produce the same bushing in 6 minutes with zero operator attention, beyond loading and unloading. Simple mathematics suggested the Berkshire shop couldn't compete. But Thomas pulled out their invoice. The bushing sold for $85. The aerospace shop charged $120 for equivalent work because their overhead demanded it. "Your machine cost $180,000 new," Thomas observed. "Required 3-phase power, specialized tooling, and a programmer who understands G-code. Our lathe cost my great-grandfather $300 in 1897. which is about $10,000 in today's money. It's been paid off for a century. We have no power bill, no software subscriptions, no planned obsolescence. Our overhead per part is essentially just material and labor. The aerospace manager couldn't argue with the economics, but he pressed on technical limitations. What about tolerances? We hold plus or minus 0.0002 inches routinely. That's 10 times tighter than what you're showing me. Thomas nodded. Absolutely true. For aerospace work requiring those tolerances, modern CNC is the only option. But look at your order book honestly. What percentage of your parts actually need that precision? Most mechanical components function perfectly at plus or minus 0.002 inches. We serve that market profitably because we don't carry the overhead required to achieve precision that most applications don't need. The manager examined the shop's other completed parts. Gear blanks, flanges, shaft collars, spacers. All were components that existed in thousands of machines across New England. All met their print specifications comfortably. None required the 5-axis sophistication or micron-level accuracy that justified modern CNC investment. You're basically running a museum that occasionally makes parts, the manager concluded, though his tone had softened from dismissive to thoughtful. Thomas smiled. We're running a business that happens to use museum-quality equipment. The distinction matters when the power goes out and you need a part. When the Colonial Pipeline ransomware attack shut down fuel distribution across the eastern United States in May 2021, panic spread through manufacturing operations dependent on just-in-time delivery. Shops rationed diesel for their backup generators. Trucking companies parked their fleets. Production schedules collapsed as the digital supply chain revealed its fragility. The Berkshire shop continued machining parts on schedule. Their raw material arrived the same way it had for decades. Bulk deliveries of steel, bronze, and aluminum bar stock stored in racks that held 6 months of inventory. No overnight shipping, no tracking numbers, no digital logistics coordination, just material purchased when prices were favorable and stored until needed. Sarah explained their supply philosophy to a business professor studying resilient manufacturing. Modern shops optimize for efficiency by minimizing inventory. They store 3 days of material and rely on overnight delivery to restock. It's incredibly efficient until anything disrupts transportation, then production stops immediately. The professor examined their material storage. Racks of cold-rolled steel, bronze rounds, aluminum plate, all purchased in bulk during market downturns. This represents significant capital tied up in inventory. Financial optimization would suggest keeping minimal stock and freeing that capital for other investments. Financial optimization assumes uninterrupted supply, Thomas countered. We optimize for continuation. When material prices spike or supply chains break, we keep producing while competitors wait. We've won contracts simply by being the only shop that could deliver during disruptions. The same principle extended to their tooling. Modern carbide inserts came from global supply chains spanning 3 continents. Tungsten from China, cobalt from Congo, precision grinding in Germany. The Berkshire shop used high-speed steel tools. They sharpened themselves on a grinding wheel that had been turning since 1919. When insert suppliers faced delays, modern shops idled their machines. The Berkshire shop ground its tools sharp and kept cutting. Even their leather belts demonstrated supply chain resilience. The belts were made by one of the last traditional tanneries in America, using oak bark tanning processes unchanged since the 1800s. When supply chain disruptions affected modern V-belts made from synthetic materials and imported rubber, the Berkshire shop simply ordered from the tannery in Pennsylvania that had supplied them for 80 years. Globalization increased efficiency but decreased resilience, the professor observed, making notes. Your operation represents the opposite trade-off, lower efficiency but higher resilience. The question is whether resilience has economic value that justifies the efficiency sacrifice. Thomas pointed to their order board, filled with jobs from clients who had learned the value of reliability. Efficiency is worthless if you can't maintain it during disruptions. Resilience looks expensive until you're the only shop still running when others have stopped. Then it looks like wisdom. The engineering students filled the Berkshire shop on a cold March morning, notebooks ready to document what their professors had called an educational curiosity. They represented MIT, RPI, and Worcester Polytechnic. institutions where manufacturing meant robotics, artificial intelligence, and Industry 4.0 integration. The sight of leather belts and water wheels seemed as relevant as studying horse-drawn carriages. Thomas let them measure, photograph, and calculate. They determined the turbine's efficiency, 92%, remarkably close to Francis's 1849 predictions. They analyzed the line shaft system's power transmission losses, 18% from turbine to final machine tool. They calculated productivity metrics that confirmed modern CNC equipment was indeed faster, more precise, and more versatile. Then Thomas asked the question that reframed everything. What happens to your advanced manufacturing when the systems it depends on fail? The students initially dismissed this as cynicism about progress. But Thomas walked them through scenarios that grew increasingly plausible as he spoke. Cyber attacks that could shut down digitally controlled equipment. Supply chain disruptions that could starve shops of proprietary components. Energy grid instabilities that could interrupt production for days. Economic pressures that could make operating costs unsustainable. We're not arguing against progress, Sarah clarified. We're arguing against total dependence. Modern manufacturing has abandoned resilience in pursuit of optimization. Everything works beautifully until something breaks, and then everything stops. She showed them contracts from clients who maintained the Berkshire shop as a backup supplier, not for everyday production, but as insurance against the vulnerabilities in their primary supply chains. These clients paid premium prices for that insurance because they understood that resilience had value that didn't appear on efficiency spreadsheets. One student raised the obvious objection, "But you can't scale this approach. Water power is location dependent. Most manufacturing happens far from suitable streams. This might work for you, but it's not replicable." Thomas agreed completely. "You're right. This exact solution isn't universal. But the principle is, don't build systems with single points of catastrophic failure. Modern manufacturing depends entirely on the electrical grid, digital controls, and global supply chains. Remove any one of those and production stops. We're not saying everyone should use water wheels. We're saying everyone should ask what happens when their dependencies fail." The students left with data supporting both conclusions, that modern manufacturing was indeed more efficient, and that the Berkshire shop's approach offered resilience that efficiency-optimized systems couldn't match. Neither approach was objectively superior. They represented different values: speed versus reliability, optimization versus robustness, progress versus persistence. As the students' cars disappeared down the road, Sarah engaged the lathe clutch and resumed cutting a bronze bushing. The river flowed beneath the floorboards, the water wheel turned, and the shop continued doing what it had done for 125 years, making parts regardless of what failed in the world outside. But one question remained unanswered, the one that would determine whether this old wisdom mattered to anyone beyond historians. Could modern manufacturing adopt the Berkshire shop's resilience principles without abandoning the efficiency that made global competition possible?